I dream I can achieve that. Damn. That is beautiful. One day, I dream I can achieve that. Damn.
You know that's not human, man.
Insanity.
I don't even know what I
so
did.
happy to see that in person. That is beautiful. One day, I dream I can achieve that. Damn.
So this video, it was the result of 7 years of work. More than 40 people were involved. What you just saw was the first AI versus human drone race, which took place in Zurich, Switzerland in June 2022, during which our AI-powered quadcopter drone outperformed 2 world champion drone racing pilots. It's a historical result. The paper was published in Nature, and it's considered the first time an AI beat a human in the physical world, in a physical sport, in a fair play. It was vision-based, entirely driven by a single onboard camera and an onboard computer. So this presentation is about Agile robotics, but let me motivate it first. Let me go a few years back in time. You may know the Roomba vacuum cleaning robot. It was the first autonomous vacuum cleaning robot that many other companies came out. What you see in this picture is a long exposure picture that was taken with one of the old-fashioned Roomba autonomous cleaners. The average cleaning time of a 20 square meter bedroom was around 20 minutes in 2018, only 7 years ago. And you can see why. The robot was quite stupid. At the end of 2018, something happened, and the robot became all of a sudden much more productive, 4 times more productive. Instead of 20, it would take 5 minutes. What happened? Well, they added a camera. The robot went from being completely blind and brainless to having a camera and a computer in his lap. Where else has perception played a pivotal role? Like locomotion. You have certainly seen this video multiple times. Is the old-fashioned atlas, hydraulic atlas, doing parkour. I don't know if you've seen how it works. It works thanks to computer vision and motor-created control. There are 4 cameras that build a map of the environment, the SLAM, they predict the next step sequence, and then they accommodate for the errors made by the circuit. Where else has perception made a change? On Mars. For the first time, NASA could actually navigate a robot on another planet. Yes, because the previous rovers were not really autonomous. They were still controlled from Earth. But to fly, you need a 50 Hertz control loop. So they had to do it for the first time autonomously. And it was entirely vision-based, with an onboard camera, an inertial sensor, and an onboard computer. So what we've seen from these simple examples is that computer vision is making mobile robots more autonomous. But when you look around, you wonder, where are the robots? You know, unless you go to Los Angeles and San Francisco and the other cities, you usually don't see robots. The reason is that we are still very far from human performance in terms of agility, versatility, and most importantly, robustness. Now, in my lab, we have been working on drones for about 16 years. Not because they are cool, but because the drone is the only platform that without seeing a single image cannot even fly. You know, if you have a car, you have a light robot, even if they stand still, they will not crash. But the drone needs to see even an image to stay still over it. Before I start, let me ask you, can you raise your hand if you are in robotics? 5 people. Okay, thank you. What we are trying to do in my lab is that we are trying to understand how we can make algorithms that can one day fly vision-based drones better than expert human pilots. What you see in this video is not an autonomous drone. It's a drone operated by an expert human pilot. And expert human pilots are not just pilots. These are people that have dedicated at least 3 years of their life flying every single day. They are specialized. They are domain experts. How do expert pilots pilot drones? Vision-based. There is a camera that transmits the signal to the goggles. The brain analyzes the images and sends the control commands to the joystick. When we started this research, we studied how human pilots pilot drones because we thought that the reason why humans are better than machines is because they are faster than machines. And we were wrong. We put eye trackers on expert pilots, 20 different subjects. We measured the reaction time over different tasks, and we measured it at around a quarter of a second. So we came to the conclusion that it is a lot, because a quarter of a second is 10 times as slow than our autonomous algorithms. So we came to the conclusion that human pilots are better than machines, not because they are faster, but because they can make better decisions in complex situations. And if you work in autonomous driving, and there is a lot of people here in this conference, you know very well why. You know, it's very difficult to build an autopilot. Humans make an accident in driving every 100 million kilometers. We are not just there yet. You know, we need perception, planning, control, a lot of stuff. Now, you may wonder, why do you, Davide, care so much about making drones more agile? It's a legitimate question. The reason why we want to make more agile drones is because a drone that can fly faster can fly longer distances. Think about a quadcopter drone. The battery can only last for 20, 30 minutes. There is not much you can do in 20, 30 minutes, but if you can fly faster, you can fly longer distances. And that's also what you see in this plot. What you see in this plot, on the vertical axis is the maximum distance that the drone can reach before running out of battery. And on the x-axis is the ground speed. As you can see, the faster you fly, the longer distances you can fly, but up to an optimal speed. Because after the optimal speed, then it's no longer convenient to fly fast. It will be less productive. So we expect that in the future, all the drones will be flying at the optimal speed. That's what you expect robots to do, to be optimal. Now, when we try to plot here the world-leading drone companies, DJI, Flyability, Skyview, they all use computer vision, by the way. They don't fly at even 1/3 of the optimal speed. Why? Because it's very difficult to fly fast. There is motion blur, there is aerodynamic effects, visual degradation. There are so many effects. On the other side, the human pilots don't really care about productivity. They just push to win a race, for example. But many years ago, we thought maybe if we try to gamify research, we can push the limits on vision-based navigation. And that's why we started working on agile drone navigation. And we know that this research will be very beneficial to many other fields, search and rescue, exploration, wildfire, especially now. All the fires that were, for example, recently in LA and every year. Drones are again research. There are, at the moment, there is 12 million award prize from Google, the famous X Prize Challenge, dedicated to drones to prevent wildfire. I'm working with NASA on the next Mars Science helicopter, planned for 2031. Of course, there is defense, but everything we know is dual use. But there is so much good that drones can do. Now, in order to understand how we can fly drones more agile, we need to understand how drones, or in general robots, are controlled. So since there are only 5 people in this room that know robotics, so robotics goes back to 40 years ago. Okay, last year we celebrated 40 years of robotics. It's very young, it's younger than computer vision. Building hardware is very difficult. So all robots that you see around us today are controlled with these 3 software modules: perception, planning, and control. Perception does what we call state estimation. So it means estimate the position, velocity, orientation of the robot, and also build a map of the environment. Then you send this information to the planning module that computes a trajectory, avoiding obstacles. And then there is the control module that computes the speed of the 4 wheels of the car or the 4 propellers for a quadcopter. Now, this architecture has been used for 40 years, so we are very happy. We have 40 million vacuum cleaning robots that are autonomous, so it works. We have 55 million drones, so we are very happy. The drone is the most sold robot, by the way, if you didn't know. We are very happy. What's missing? Well, this architecture is fragile to imperfect perception and non-model effect, and it's also very slow, especially when you fly fast. You have motion blur, you have overexposure of the camera, you have aerodynamic effects. You know, aerodynamic effects, if you are in computer vision, you understand this too very well, I'm sure. But what about these ones? You see these vortices? Here, the drone was flying at 70 kilometers per hour, and these vortices are very difficult to model. If you are familiar with computational fluid dynamics, you can run those models, and then you get a very good estimation of these vortices. But they take several hours to days of compute, and they depend on the trajectory of the drone. We want to run these things at 50 Hertz. Okay, so can we find something better? Yes, we can. On the other side, human pilots use neural networks, and they can map directly control sensory inputs to control commands. There is many research groups around the world that are focusing on end-to-end architecture, and some of them are quite successful. We were also successful, but eventually, when you deploy a robot in the wild, it has to be 100% robust. So if something fails, you need to be able to tell the person that was killed or injured why that case fails and which part of the arena failed. So they lack interpretability. Another problem with the end-to-end networks is that they need a huge amount of data to train. So they are not sample efficient. So what we have done over the past 7 years is trying to combine model-based approaches with deep models. But the problem is when you start integrating deep models, there are 3 key questions. Should you train with or without supervision? And where do you get trained data? Well, it turns out you can actually use data in simulation. Simulation is fast, it's cheap, and it's safe. But then when you train data only in the network only in simulation, there is a sim-to-real gap. There is no guarantee that something trained in simulation will transfer to the real world. Well, we were able to only train in simulation and transfer to the real world without any fine-tuning, but it wasn't easy. Now, rather than working on abstract concepts, we took 3 tasks that are not the most useful, but they were useful to us researchers to push, to measure our progress with respect to human pilots. So we picked acrobatic maneuvers, navigation in unknown environments, and drone racing. But we also had to build a very agile drone. So 7 years ago, we reached out to Marvin. Marvin was a boy, 15 years old, the Swiss champion of drone racing. He was this small. And he would always come to us with his father, because of course he was a minor. With Marvin, we started a brilliant collaboration. We built this drone that is super agile. It can accelerate from 0 to 100 kilometers per hour in 0.7 seconds. A Formula One takes 2.6 seconds. It achieves accelerations of 5G. When you are on a roller coaster, it's exactly what you experience. We have NVIDIA Jetson, now Orin, by the way, and we have interior sensor eyes. The drone is about 20 centimeters in diameter, so about this size, very small. Well, let me show you a few cool videos. This is our drone performing acrobatic maneuvers, just using a camera and an onboard computer. No GPS, no motion capture, completely autonomous. This one has a single neural network that takes as input feature tracks, so KLT features, and outputs directly control commands. Not only was it as agile as a human expert pilot, we could also execute these maneuvers backwards, where human pilots struggle. But for the machines, you just revert the policy. Very easy. This was the same drone, now slaloming among forests up to 40 kilometers per hour. And we achieved this at twice the speed than previous model-based approaches. Now, the nice thing about this is that both relied, in a way or another, on hybrid approaches, so meaning standard and deep, or just deep, and they were entirely trained in simulation without any fine-tuning in the real world. How was this happening? So the network consumes images. Now, if you train, now I'm not going to show you the details because it would be another hour and I want to talk about something else. But what we found out is that if you train neural network models on raw image pixels and then you transfer to the real world without any fine-tuning, the success rate is going to be 0. So the trick was to train these models on an abstraction of the images, which depends on the task. For acrobatics, it was optical flow or visual tracks. For slaloming in a forest, it was depth maps. You understand why the transfer without any fine-tuning? Because these are representations, intermediate representations that are very similar between simulation and the real world. Okay, I'm sure you have a lot of questions. We can come to this later. You can ask me, how do we know in advance what's the suitable representation? Can you learn it? Yes to each question. You can. Now, let me go to the things I'm actually most excited about. So these works relied on hybrid model-based and or deep models, and they were trained with imitation learning. So we were imitating an expert algorithm, the best artificial algorithm, which means an expert existed. Now, there is a task where an expert cannot be designed, and that's why we got super excited about drone racing. Drone racing is a task where you cannot design an expert, and certainly you don't want to ask a human to be their expert because you want to be better than humans. So let me introduce you to Marvin so that you understand why drone racing is so difficult. So we took this video 7 years ago when Marvin was only 15 and coming with his father all the time, sometimes skipping school, so we're very thankful to him. Let me run the video.
Get ready on the top. Less than 5. Beep.
You see how did you see how close Marvin goes to the edges of the gates? I find this always impressive. They don't really maximize safety, they maximize their chances to win the race. And I find that amazing. So this is a sport where the only metric is the lap time. So how long it takes to finish the race, like in Formula One. But it's more difficult than Formula One because they fly in 3D. Now, in this sport, there is no time for thinking. It requires really, very quick decision making. And any small distraction, any small error can lead to the loss of the race. Now, when we started working on drone racing, we thought that the problem was easy. How did we face the problem at the very beginning? So in drone racing, you are overfitting the task, which means training and testing environment are identical. Human pilots, they get to practice in the same track where they will compete. Usually they get access a few days to a few weeks before the competition. In the American Drone Racing League, that is so big and so rich as an organization, they only have private pilots that are full 100% paid by the association. They get a simulator and they get a CAD file of the layout where they will race in the real environment. So that's crazy. That means, given that you know perfectly the environment with millimeter precision, you can solve the problem. Look at this animation by trying to compute the truly time optimal trajectory, which is the trajectory that is guaranteed to be superhuman. Does it make sense? Now, we thought the problem was easy. We dedicated 7 years of classic control algorithms and estimations to this problem, but we were always a little bit below the performance of human pilots. I think we reached the highest excitement point when, after 4 years, we invited the 3 best pilots and Marvin. We outperformed them and we were super excited. We wrote a press release, was published in Fox, but then we were wrong. A world champion pilot came originally from Switzerland, saw our news in the news, that's why it's so important to publish lots of press releases. He said, Davide, I'm passing by to visit my mother. Can I come to your arena and race on the same track you published about? They said, sure, Gabriel, come. Gabriel Coffee. And then he came, and his performance was better than our, at the time, superhuman drone. So our excitement went down. And then, well, we didn't know what to do. It was already 4 years after working on this on optimal control. A lot of the good publications published also the science as well, transactions of robotics. We didn't understand what the problem was. Well, let me show you the problem. The problem is the perception residuals, what you cannot capture in your modeling. And that's just one part of the problem, by the way. So this is our eventual superhuman champion of autonomous drone outperformed Alex Van Over 3 years later in that event. This is how it works. So we are relying on egocentric vision. We have a single camera, the same camera human pilots use. Now, how can you estimate the position, the orientation, and velocity of the drone? Well, you can use PNP. You detect the gates, you detect the 4 corners of the gate, you triangulate the gate position. We know this algorithm for 40 years, we know how to do that. Fine. But there is a problem. You see this ellipsoid. This ellipsoid is called the ellipsoid of covariance. Is the uncertainty about the position and orientation of the drone. The farther you are from an object, the larger is the covariance. You may know, if you start with the classic computer vision, that the ellipsoid of uncertainty scales quadratically with the distance from the object. There is not much you can do. The problem is that no controller can deal, no classic controller can deal with such a varying state uncertainty. And this was just one of the problems. Another problem was that there was a lot more of effects. For example, the camera was sitting on a different frame than the quadrotor with dampers to isolate the vibrations between the motors and the camera. And these dampers were getting compressed up to 1 centimeter, causing errors in the estimation of visual odometry of up to 2 meters. This is to say that while we were working on classic control algorithms, we also explored reinforcement learning. But now, and this was actually the work of Yulong Song, who strongly believed in that, and he was right. While the other 4 PhD students were working on classic control, 1 PhD student was working on neural network controllers, trained in simulation with the model-free deep reinforcement learning. In simulation, we learn from trial and error. How long did it take? 21 million episodes. How long is that? It's like having a single drone flying continuously without any interruption for 60 consecutive days. How long did it take? 60 minutes. How long does it take today? 20 minutes. Let me show you in 10 seconds a time lapse of the learning process in simulation. Each of these green vehicles is a drone. So we simulate, we use a massive parallelization in simulation. We simulate 100 drones that are learning to fly by trial and error. You'll see, before I play the video, you will see that every time they crash, so you see the trajectory attempted by the drone in yellow, and they will crash billions of times. At some point, you will see that the drones will be hovering, so they start to learn to hover, then to fly, and then to race. That's it. So at the beginning, they're just going at random, right? The weights of the neural network are initialized at random. Now look what is happening after 40 iterations. Basically, they start to learn to hover. Now look, they start to learn to pass through 1 gate, then 2 gates, and 3 gates, then all the gates. Then you let it run for 21 million episodes, and then you get this. You get superhuman performance. Let me show you this. What you see here is the progress of the reward as a function of the simulation time steps. I told you 20 million episodes, but 10% of the episodes are needed to learn to fly fast. So if I stop the training process after 10%, so say 1 minute, and you let it fly, you would think this guy is flying super fast. But when I, like mine, as an expert, I tell you, it's pretty good, not bad, it's like Marvin. But if you let it train for another 90% of the samples, you will learn to fly better than the best champion human pilot. Then we went back to, we talked to psychologists, biologists, and they told us, well, Davide, it's very similar to how we learn to walk, then to run, and then to race. It takes humans 1 year to learn to walk, a few more years to run, and many more years to race, and some people, a few people even to race us for a change. So there is some analogy to humans there. For me, the great story was that, we were so much insisting with classic model-based controllers, but we were always a tiny bit of the performance of the best champion. So after 7 years of work, my student Yulong was super excited, and by the way, he was always confident. So he was confident at the level that you would trust him, even though me as a director or researcher said, okay, take it with a grain of salt. But anyway, I trusted your love. Everyone trusted your love. We decided to invite to Zurich Alex Van Over, who is the world champion, who was the world champion at the time of the drone racing league. And we invited Thomas Mitmatta, who was the world champion of the multi-JP international league. So there are 2 main leagues in the world. We invited Martin because he was the local champion, Swiss champion. And then, of course, our AI drone, which we named Swift. The important thing is that we had a fair race. So the human piloted drone and the autonomous drone were identical. So we built the drones according to the specifications of Alex Van Over, which we knew, is very good. He plays now for Hollywood. Ambulance, Gran Turismo, Red Notice, they were all shot by Van Over. So the drones had the same mass, the same aerodynamics, the same camera, the same field of view, everything was the same. The only difference was that one had a computer on board, the other one did not. But the weight was identical. The important thing is we let the human practice on the racing track for 1 week, every single day. So they had access for the entire day, also at night if they wish. Also, when we organize the competitions at the end of the training, we invited 1,000 people. That's very important because these people want to get the adrenaline that they would have in a real game. You give your best performance when someone cheers up for you. So that was important to have an audience. Let me show you the footage we recorded of one of the competitions. So Swift won with a lead time of 0.5 seconds, which is a lot, because in these competitions, typically the difference between the first and the second place winner is about 0.1 seconds. Also, Swift recorded the largest amount of wins, 15 out of 25, so 60% of the races. The results were published on simulation data. When we deployed the policy learned in simulation in the real world, we could not outperform Alex Van Over, who was the best of the 2 champions. And you see why. Here you see the famous simulation to reality gap. Sometimes it's difficult to render the simulation to reality gap. Here it's very easy. One of the 2 trajectories is simulated, the other one is the actually executed one. In the largest point, which is here, the error is about 2 meters. You have to consider this track was 300 by 300, sorry, it was 30 by 30 meter wide. So it was not sufficient to train in simulation. We needed to collect additional data in the real world and fine-tune the policy in an improved simulator with data collected in the real world. So what we learned, and that's the key lesson of this paper, after we trained the policy for the first time in simulation, we deploy it in the real world with a motion capture system. And we do that to record the residual models of perception and aerodynamics. In particular, the residual models due to perception due to systematic errors, and also for aerodynamics for the turbulences that we cannot explain by first principles. Then we use these ground truth trajectories to learn a neural network model that models the discrepancy between the first principle model and the ground truth one. We add this neural network model in our simulator, so you can say we are learning the residual of our simulator, but it's not a residual specifically for that task. Then we fine-tune the policy in this improved simulator. It only takes 1 or 2 minutes more, because we are just fine-tuning. And finally, we deploy it in the real world. And that was when we outperformed Alex Van Over. This was the first takeaway of this research, 7 years of work. The second takeaway, which is the one we are most excited about, and we received now a lot of interest by the community. In the second paper, the Science Robotics paper, we delved into the reasons of why reinforcement learning outperformed optimal control. You see, we spent 7 years in optimal control. Everyone is working on optimal control for building autonomous race cars. But actually, we came to the conclusion that, RL is better than optimal control. And we did a lot of evaluations there in simulation in the real world. And the main conclusion was that reinforcement learning beats optimal control because it optimizes a better objective, a non-differentiable objective, which is a task-level objective. You see, in optimal control, you require a continuous differentiable objective, typically expressed as an error with respect to a reference trajectory. Sure, but who gives you the reference trajectory if you want to be superhuman? That's the first question. Instead, in reinforcement learning, you just tell it, I want to minimize the my lap time and minimize crashes. That's it. Also, another reason why RL performed optimal control is because RL exploits domain randomization. So you expose in simulation the controller to all the features you wanted to cope with in the real world. For example, the non-Gaussian noise of systematic errors, motion blur, and all that stuff. And by doing so, the controller becomes more robust to discover, things that the optimal controller cannot. By the way, if you're interested, I can also show you the maneuvers that Swift learned by which the human champions lost, but I will not show it for reasons of time. Now, when I show these videos, people say, okay, but is there, therefore, the game over? Is AI better than humans now in the race? Absolutely not. You see, the results were run in a controlled environment. We are scientists. It was in a hangar. We controlled the illumination, controlled turbulences, controlled wind. So, we have to be careful to say we outperform human champions in any situation and in any track. Still, we are certainly very far away from human expert pilots in robustness and versatility, which means generalizability to any task. You take it to a different environment. Thousands of times a year. Okay, so you need to repair, it takes a lot of time, and so on. But we are not the only ones. To make Atlas do parkour, the one time they went through hundreds of failures that you may have seen. So when you ask me where are we compared to human pilots, well, I think we are here in terms of agility, but human pilots are still the best solution, and that's why they are the only option at the moment. And our vision is to be better than human pilots. That's also what autonomous car people want to do. Now, looking farther, what can we do? Who's going to be better than human pilots? So now this is much more an outlook. Birds. Birds eventually are better than human pilots. Why? Because birds have their eyes directly on the aircraft. You see, human pilots do not sit on the aircraft. Human pilots have a camera that streams images at 30 Hz to their screen on their hand-mounted display. So they consume images coming at 30 Hz. If you could teleport yourself on the drone, you would not only sense the drone, but most importantly, you would see a continuous stream of information coming from your radios, which are not frame-based, they are continuous in time. You see, the agility of a robot depends only on the latency of its sensors and algorithms. If you want to have a more agile robot, you need a very small latency. So typically, you would like to have a latency of 1 millisecond. We don't have that with frame-based camera. The latency is 30 milliseconds. How can you achieve a 1 millisecond latency? Increase the frame rate. If you have a frame rate of 1000 FPS, you have a 1 millisecond latency, right? What's the price you pay? There is no free lunch. Bandwidth. Bandwidth is inversely proportional to the latency. You know this very well. It's the famous bandwidth latency trade-off. If you want to reduce the latency, you do this at the expense of the bandwidth. If you want to reduce the bandwidth, you do this at the expense of the latency and at the expense of safety. Is there a sensor that allows you to have an arbitrary latency and an arbitrary bandwidth? Yes, it's the event camera or neuromorphic camera. It's the only visual sensor that allows you to arbitrarily choose the bandwidth and the latency. What is an event camera? An event camera is a sensor that measures only motion in the scene. Here I'm moving my hand in front of the camera, and you can see that only the pixels that trigger motion trigger events. If I move the camera with respect to the environment, edges again trigger events. But these events are not triggered at frame time, they're triggered continuously in time. Let me explain that better. Look at this animation where I have a rotating disk. What will be the output of the event camera? Will be a spiral of events in space and time. Why? Because only the pixels that detected the rotation or motion of the dot trigger the information, and that's the beauty of the sensor. So the information comes only when something is moving. If nothing is moving, there is no information transmitted. And there is also no motion blur. So an event camera has three key advantages: low latency, the order of microsecond resolution, low bandwidth, negligible motion blur. Most importantly, the information is streamed continuously rather than a frame-based. Now, what we have done over the past 12 years, so we were among the first groups to have access to event cameras. They were invented in 2008. They became commercial. They were then available to beta testers from 2012, and they became commercially purchasable in 2014 or 15. So we were one of the first groups to work with them. Well, we showed that with event cameras unlock scenarios that are inaccessible to standard cameras. So one of the first things we did many years ago was to extend the Lucas-Canade tracking algorithm to event cameras. You see, Lucas-Canade works with standard frames. Well, we managed to extend the Lucas-Canade to events. Well, now you can track features in the blind time between two frames. And that's already, human level. You can do continuous feature detection and tracking. And this was actually the key fundamental step for an SLAM algorithm, structure for motion algorithm. And we showed the key advantage of an event camera in this demonstrator, which we also demonstrated at CVPR 2018-19 if you were there. So it's the famous lasso sequence. Here, my PhD student firmly attached the event camera to the USB cable with the tape, and then it spinned the event camera super fast like a cowboy. So the standard camera detects nothing because it's too motion blurred. The event camera sees edges. We can detect and track features, and you can use these features to do visual modeling. This was essential to our drone-related research. Let me show you something that is pretty cool for robotics researchers. What happens if a drone loses a motor? What happens? The drone starts spinning on itself and eventually crashes. Let me show it. So here we induce this failure of one motor. Because of all the three motors working, now the drone starts spinning on itself like a ballerina. Then you lose control and it crashes. Well, we prevented it from crashing. So the drone keeps spinning on itself because of the principle of conservation of the angular momentum. But we were able to sustain flight because we are using an event camera, which is not affected by motion blur. Here you see the raw events. And here are the processed events where we were doing visual detection and tracking. And here you see the standard frames that are super motion blurred, especially the motion blur is major at the periphery of the image and almost zero at the center. That's why all the features are localized in the center. But if you try to do state estimation visual odometry with a standard camera, you'll fail because of motion blur and the drone will crash. But with the event camera, we were able to actually sustain flight, do unstable hovering, so the drone remains spinning on itself on the current spot. Then we went farther than that. Let me show you that. It's really cool. What comes next? We went outside, and we were able to control the drone to follow a straight line trajectory. So go forward and come back, all while spinning. You cannot stop the spinning, it's impossible, okay? It's physically impossible, but we avoid crashing. So we released the code open source because we said, look, there are so many commercial drone companies, this can be good for our society. In Zurich, we had 2 drone crashes by the company Mothernet, and one of them was close to a kindergarten, and it was caused by a model failure. So, these things can save a life. This is another research we did on dodging obstacles thanks to event cameras. Here, the drone is in forward flight. So there is a relative speed of up to 10 meters per second, which is a lot, 36 kilometers per hour. And the drone was able to execute the evasive maneuver very last minute. How was this made possible? Well, look at the rendering of the events in the 2D and in the 3D spatial-temporal domain. Now let me zoom in the space-time domain. Be careful, watch. There you go. You can zoom in the events domain, the time domain, and you can see that the ball leaves a trace of events. The events generated by the ball, so by the moving object, they are 10 different temporal statistics than events generated by the stationary background. So you can tell them apart. And we could do this with a latency of 3 milliseconds, which if you wanted to do with a standard camera would require 300 frames per second camera and also GPU. We did this with an Android CPU, a Samsung Smart Galaxy S4 computer. So I'm really excited. This is not my research, this is from Boeing. Boeing now has 3 event cameras in their production line. This is a paper Boeing published 2 years ago. This is a mock-up wing. When you produce a wing, there are many holes, and they need to measure the diameter of each hole to make sure that they are within the tolerances. Typically, they do this with a standard camera, but you need to pose the standard camera in front of each hole, which takes a second per hole, more or less. Now they do this with the event camera and they don't stop. So they basically save 10 times the inspection that they were doing before. And this is very exciting. Almost done. What's for the future? So if you look at the past 10 years of research of event cameras, they were dedicated to event cameras alone in isolation. But over the past 3 years, we started witnessing more and more research trying to combine the benefits of event cameras with standard cameras. Because you see, event cameras see well at high speed, but not well in low speed or zero speed. But standard cameras are good at low speeds. They also have a higher spatial resolution. So the two sensors are perfectly complementary. And this is research we did at my lab, and also this is a famous video from the company Prophecy, one of the largest companies on event cameras. What do they do here? This is a paper that just appeared also on Bali. They use frames and events to unblur blurry videos. So here, so this is a snapshot before and after the event, the blurring. Now there are many smartphone companies like Xiaomi, Oppo, Huawei who are interested in this type of things, and there have been many prototypes also showcased at CVPR in the past editions where they would give live demos of this. Another thing we're working on is automotive, trying to detect the traffic participants faster than any camera. And this is also another exciting research that we recently published in Nature, where we managed to do interframe object detection of pedestrians, cars, bicyclists, and other vehicles. And we managed to do this with a latency of 0.2 milliseconds, either using events or standard frames, or the combination of both. I will not go into the details, but what made it possible is an asynchronous graph neural network, which now we are trying to implement on an FPGA. And what we show is that if you combine an event camera with a 20 FPS camera, you get the same latency as a 5000 FPS camera, but with a bandwidth of a 50 Hz camera, which is quite exciting in my opinion. And with this, I would like to thank you for your attention. Thank you.
Davide, so we have some time for some questions. In the meantime, Boris, if you can install it. That's all. You can go to the microphone here.
Amazing work. One question I had is, have you looked into like long sequence of event camera data and compression of it, and how the fact that it is non spatially correlated, maybe temporally correlated, you see what kind of compression algorithms may work for it?
In fact, yes, we did that work. Actually, let me see if I have the slides ready for that. Yeah, actually, yeah, this is a video frame decoration. Here we go from 100 FPS to 5000 FPS, so an sampling factor of 50. This one combines event cameras and standard cameras. So we have a compression rate of 40. So this is actually something that excited quite a lot Sony, because it could potentially, it holds promise to enable video calling with much less data, bandwidth, savings with respect to the current video calls, without sacrificing accuracy. So that's something that holds promise for that. So yes, it is compressive sensing that the sensor is working.
You're extrapolating the RGB to higher frame rate.
No, we are not. It's compressive because the event camera directly encodes the changes of light over time, the temporal derivative. So it's not doing a detection effective, it's doing a temporal derivation. And then here what we do is that we have an attention network that decides from which source of data we estimate the optic flow, whether the RGB or the events. And